This is a video on the subject of linear interpolation in a steam table. If we look at example 2 there, we can see that on the slide we're given two sets of information, basically at two different pressures. So we have a pressure of 1 megapascal, and you can see that 200 degrees C corresponds to a specific volume of 0.2060 meters cubed per kilogram. 240 degrees C corresponds to a specific volume of 0.2275. Likewise, 280 degrees C corresponds to a specific volume of 0.2480. Then we have a second set of data at a pressure of 1.5 megapascals with the corresponding temperatures and specific volumes. So this is real data. It's not from a model. It was found by experiment, and it's put in this table. And it's actually quite helpful. There's tables in the back of Felder that show thermodynamic data for steam. It gives internal energy, in particular specific internal energy, so on a mass basis. And it also gives enthalpy, and it gives specific volume. So in this case, part A is asking for essentially a value that's off this set of data, or it's off this table. We want to find the specific volume in meters cubed per kilogram at a temperature of 240 degrees C, but at a pressure that's between the two pressures given. The pressure is at 1.25 megapascals. So we have to do some interpolation to do this. And essentially what interpolation is taking two different points, drawing a line between them, and figuring out where between those 2 points on that line does a property of interest lie. So if you look at the points and data we know, we can see our slope here is generated by just our simple y1 minus y0 over x1 minus x0. And we're setting that equal to the same slope here, except we're at our x and y value of interest. So what we'll do is we'll put in our x value that we want the y value at. So in this case, we'll put in our 1.25 megapascals, and the y value will be our specific volume of interest in meters cubed per kilogram at 1.25 megapascals. So if we take this format and think about our point slope format, we have y, x, some introductory point here, and then our slope. So the slope, again, is calculated by taking those 2 points, forming a line between them. And then when we kind of combine these two forms, we have y equals y0. So in this case, y0 will be 0.2275 meters cubed per kilogram, because we'll be going between 240 at 1 megapascal and 240 at 1.5 megapascals. So let's look at this. We want to find it at 1.25 megapascals. So that means that y is equal to 0.2275 meters cubed per kilogram plus 0.1483 minus 0.2275 meters cubed per kilogram times 1.25 megapascals, which is our pressure of interest, minus 1.0, and that's our x0, divided by x1, which is 1.5, minus 1.0 megapascals. So if we evaluate this, we end up with 0.1879 meters cubed per kilogram. And sure enough, this lies between 0.2275 and 0.1483 meters cubed per kilogram. So we know it's a reasonable pick for the data at 1.25 megapascals, 240 degrees C. So that's for part A.